Behind him stood countless unnamed technicians doing the same, solving life-and-death problems with the tools of a repairman, not the budget of a lab. They worked in maintenance tents lined with frost, surrounded by the hum of generators and the smell of oil. They weren't chasing recognition. They were chasing survival. At its core, the problem was thermodynamics. Every vacuum tube relied on a glowing filament, a tiny wire that heated the cathode, allowing electrons to flow. If that filament cooled, emission stopped and the radio went dead. Traditional designs assumed air temperatures between 0 degrees C and 25 degrees C. But above 35,000 feet, cockpit temperatures dropped below 50 degrees C, even in insulated aircraft. No design manual had prepared engineers for that. The sergeant's innovation, a self-regulating heat jacket, was crude but brilliant. It functioned like an early thermostatic control. By wrapping a fine resistance wire around each tube and connecting it to a separate low-voltage circuit, he ensured a constant ambient temperature inside the radio housing. The idea mimicked the principle used later in modern avionics: thermal stabilization through feedback. The modification didn't require new parts, only ingenuity. It could be installed on any existing set, from the SCR-274N to the newer VHF SCR-522 radios used in P-51 Mustangs. In laboratory terms, it violated every safety specification. But in the field it worked, reliably, consistently, and cheaply. Engineers later discovered that this method reduced the tube failure rate by nearly 70% during long-duration missions. More importantly, it stabilized frequency drift, the gradual shift in radio signals that had previously caused garbled messages at altitude. It was a reminder that innovation in war is often about subtraction, not addition. The sergeant didn't invent a new radio. He made an old one survive in a place it was never meant to exist. Within the rigid hierarchy of wartime research, ideas flowed downward, not upward. Sergeants weren't supposed to solve physics problems. That was the domain of officers and contractors. So when his reports reached Wright Field, the response was predictable: unverified modification, unauthorized, not to be implemented fleet-wide. Yet the evidence grew impossible to ignore. Pilots flying modified aircraft began submitting debriefs noting stable communication at 38,000 feet and clear transmission across full formation. Word spread through squadrons faster than paperwork could keep up. By the time official test crews evaluated the concept, it was already in use across several combat units, an underground innovation that had quietly changed the rules of engagement. For the military bureaucracy, it was an embarrassment and a revelation. The chain of command realized that sometimes the best answers came from the bottom. Wright Field engineers refined the design, adding protective insulation and standardized connectors. By mid-1944, the field heat stabilization kit became a sanctioned upgrade for new production radios. What had begun as one man's after-hours experiment became official doctrine. For the men in the air, this small technical victory felt monumental. Suddenly, voices carried where once there had been silence. Pilots could coordinate attack runs, squadron leaders could call abort signals through storm clouds, and perhaps most importantly, a young airman could hear the calm tone of his commander in the chaos, a thread of human connection through the static. In countless bomber logs, there's a subtle change after 1944. Mission reports once filled with radio failure now spoke of clear comms throughout. It wasn't dramatic, but it was decisive. At 40,000 feet, amid the thunder of engines and the glare of the sun above the clouds, that small miracle in hearing another human voice what meant everything. By mid-1944, that reckless experiment had transformed from rumor to regulation, but the real measure of its impact wouldn't be seen until the sky's over. Germany turned black with flak, and the men who relied on those radios faced the full fury of the Luftwaffe. Reliable communication at 40,000 feet didn't just save lives, it reshaped the entire language of air combat. Before this breakthrough, aerial warfare was largely visual. Pilots relied on hand signals, wing waggles, and pre-mission plans. In combat, those methods failed the moment smoke or cloud cover filled the sky. But when radios finally worked in the thin air above Europe, a new dimension opened, one of instant command, coordinated defense, and synchronized attack. In early missions, bomber formations moved like flocks of birds, held together by routine and hope. Once radio contact failed, leadership dissolved. Lead ships couldn't issue corrections, and gunners couldn't warn of fighters diving in from above. With reliable communication, that chaos vanished almost overnight. Now lead bombardiers could direct entire squadrons with precision. When enemy fighters approached, warnings rippled across the formation instantly. Bandits at 4 o'clock high wasn't a shout through glass anymore. It was a calm, clear command across dozens of aircraft, each reacting in unison. The difference was dramatic. Bomber losses in 1943 had reached catastrophic levels. Some missions saw over 20% of aircraft shot down. But by mid-1944, with upgraded communications and long-range escorts equipped with stabilized radios, survival rates improved markedly. Fighter groups could shift positions, plug defensive gaps, and redirect to intercept Luftwaffe formations in real time. The battlefield was no longer a sky of confusion. It became an orchestra of voices, each movement guided by a single rhythm. Reliable radios also allowed a new kind of precision bombing. Targeting officers in the lead ship could call exact bearing and altitude changes during the run, adjusting for wind drift and cloud breaks. Bombs that once scattered over miles now fell in tight clusters. Communication, once invisible, had become a weapon. At the command level, this new reliability changed how generals planned missions. Before, operations depended on preset routes and rigid timetables. Once bombers took off, headquarters had little control. If weather changed or the target moved, there was no way to update the crews mid-flight. But with stabilized VHF communication, commanders could redirect formations in the air. They could abort missions, call diversions, or coordinate fighter rendezvous on the fly. During the Ploiești oil raids and later strikes over Germany's Ruhr Valley, this flexibility proved invaluable. When cloud cover obscured primary targets, bomber leaders received live instructions to move to secondary ones, sparing fuel, lives, and wasted ordnance. Even the Luftwaffe noticed. German intercept operators reported unusual coordination among American formations. Noting that enemy communication appears unaffected by altitude, behind the scenes, the Allied command quietly credited the improvement to equipment reliability, upgrades. But the truth was more humble. It began with a single field, mechanics modification that allowed every signal to survive the cold. For the men inside those aircraft, the difference between static and voice was the difference between fear and focus. Before the fix, isolation at altitude was one of the war's most haunting sensations. Crews described the cockpit as a glass coffin of noise. You could see your friends in the other planes, but you couldn't reach them. In that silence, every shadow looked like an enemy, every flicker a threat. After the new radios arrived, the air war felt human again. You could hear your leader's steady breathing before he spoke. You could call for help and expect an answer. You could warn someone about enemy movement before it was too late. It's hard to measure morale in numbers, but it's written between the lines of mission diaries. Good comms all the way. Felt like we were finally working as one. Could hear the boys clear as day, felt safer. Communication, it turned out, wasn't just tactical. It was emotional. It gave shape to the invisible bond that held men together in the coldest, most hostile place on Earth. While the Allies were solving the high-altitude communication crisis, Germany faced the same problem with fewer resources. The Luftwaffe's FUG-10 and FUG-16 radio systems were technologically advanced, but notoriously sensitive to altitude and cold. Their vacuum tubes also suffered from freezing and drift. German pilots often switched to secondary frequencies mid-combat or relied on visual signals, especially during high-altitude interceptions of American bombers. Behind him stood countless unnamed technicians doing the same, solving life-and-death problems with the tools of a repairman, not the budget of a lab. They worked in maintenance tents lined with frost, surrounded by the hum of generators and the smell of oil. They weren't chasing recognition. They were chasing survival. At its core, the problem was thermodynamics. Every vacuum tube relied on a glowing filament, a tiny wire that heated the cathode, allowing electrons to flow. If that filament cooled, emission stopped and the radio went dead. Traditional designs assumed air temperatures between 0 degrees C and 25 degrees C. But above 35,000 feet, Cockpit temperatures dropped below 50 degrees C, even in insulated aircraft. No design manual had prepared engineers for that. The sergeant's innovation, a self-regulating heat jacket, was crude but brilliant. It functioned like an early thermostatic control. By wrapping a fine resistance wire around each tube and connecting it to a separate low-voltage circuit, he ensured a constant ambient temperature inside the radio housing. The idea mimicked the principle used later in modern avionics: thermal stabilization through feedback. The modification didn't require new parts, only ingenuity. When the Second World War erupted in 1939, aviation was already transforming the nature of war. But there was one invisible front that every airman fought before he even met the enemy: the battle for communication. By 1940, aircraft were climbing higher than ever before. Bombers like the B-17 Flying Fortress and fighters like the P-38 Lightning soared beyond 30,000 feet. Where the air was thin, the cold was merciless and human breath crystallized in seconds. Up there, the horizon stretched forever. But radios, and the one link between life and death, became unreliable, distorted, or completely silent. At lower altitudes, early HF, high-frequency radios worked well enough. Pilots could talk to each other, hear commands, and coordinate formations. But above 25,000 feet, strange things began to happen. Words dissolved into static. Carrier waves drifted. Circuits flickered. It wasn't incompetence, it was physics. Vacuum tubes, the delicate glass hearts of WWII radio sets, depended on controlled heat. But in the thin, freezing air of high altitudes, those tubes couldn't stay warm. As temperatures dropped to 40 or 50 degrees C, the filaments inside them became brittle, sluggish, and prone to failure. The result? A bomber group of hundreds of men, flying blind. Inside those formations, discipline broke down. Squadrons drifted out of position. Fighter escorts lost contact. Bombing runs missed their marks by miles. In a war where precision meant survival, radio silence was deadly. The U.S. Army Air Forces and the British Royal Air Force both faced this crisis. Early in the war, engineers on both sides of the Atlantic struggled to adapt existing radio designs. Sets like the SCR-274N and the British TR-9D for high-altitude operations. But no matter how they reinforced the insulation or increased the power supply, the cold simply swallowed the signal. One RAF report in 1941 described the problem bluntly. Radios function perfectly at sea level, but fail after 10 minutes of flight above 28,000 feet. Tubes freeze, circuits slow, and pilots are rendered mute, and mute meant vulnerable. In late 1942, during the Allied bombing campaigns over occupied Europe, this vulnerability turned catastrophic. Many bomber crews never received orders to change course when Luftwaffe interceptors were detected. Fighter escorts couldn't warn of attacks forming below the clouds. Lives were lost not just to enemy fire but to silence. To the generals, the issue seemed purely technical. To the engineers, it was a riddle of materials and temperature. But to the men in the cockpits, it was something more personal. The feeling of isolation at the top of the world, cut off from every familiar voice. The U.S. Army Air Forces began assembling specialized units of technicians, radio mechanics, electricians, and radar men, tasked with finding a fix. These weren't officers or scientists, but enlisted men with hands scarred from solder burns, who worked in hangars lit by single bulbs through the night. Among them was a quiet sergeant stationed at Wright Field, Ohio, a man who would soon propose an idea his commanding officer dismissed with a laugh. He wasn't from a university. He wasn't an engineer by degree, but he had the kind of intuition that could only come from fixing hundreds of broken radios in the mud and cold of airfields. As Allied bombers climbed higher and missions grew longer, the pressure mounted. Every squadron demanded a solution. Radio production bottlenecked. Commanders wrote urgent memos to Washington, calling for altitude-qualified communication systems. The war's outcome didn't just depend on bombs or bullets. It depended on whether a pilot could hear his wingman or not. And somewhere between the official research labs and the frozen skies of Europe, that one sergeant began working on a concept that everyone told him would never work. But first, to understand why his reckless idea mattered, we need to see how close the Allies came to losing control of their own airwaves. By 1943, The Allied air war over Europe had turned into a contest of endurance, not only in fuel, guns, or armor, but in communication. Every mission flown by the 8th Air Force from English airfields depended on coordination. Bombers moved in tight box formations, hundreds of aircraft strong. Fighters like the P-47 Thunderbolt and later the P-51 Mustang escorted them across the North Sea and into German airspace. But when radios failed at altitude, those vast formations became scattered flocks, easy prey for German interceptors that attacked from above and behind. Reports from returning crews told the same story again and again. Lost contact with lead ship at 27,000 feet. Command frequency unreadable. Heavy interference. Unable to relay recall signal. Formation continued beyond target. Commanders in England were furious. Engineers at Bell Labs, Collins Radio, and Western Electric scrambled to understand the issue. They tested components inside vacuum chambers chilled to simulate stratospheric conditions. They ran frequency stability trials, rewired amplifiers, and insulated cables with new materials. Still, the failures persisted. The problem wasn't just temperature, it was pressure. At 40,000 feet, air pressure is less than a quarter of sea level. In that environment, electric current behaves unpredictably. Ionization occurs more easily. Arcing and the flashover of electricity between contacts becomes dangerous. Radios built for normal conditions simply couldn't survive the thin air. By late 1943, scientists at Wright Field and Harvard Radio Research Laboratory were pushing the limits of vacuum tube design. They experimented with miniaturized valves, gas-filled tubes, and pressurized casings to keep the elements stable. Some improvements worked in the lab but failed in combat conditions. Meanwhile, in the field, enlisted technicians improvised with what they had. They wrapped radios in insulation blankets. They redirected warm air from the cabin heaters into the radio compartments. Some even built makeshift enclosures out of spare metal and rubber, desperate attempts to keep the circuits alive. It was around this time that one young Army Air Forces sergeant, assigned to a maintenance unit, proposed something radical. He suggested adding a self-heating mechanism directly to the radio tubes, a built-in resistance coil that would maintain internal temperature regardless of altitude. The idea sounded reckless. To his superiors, it meant deliberately overloading fragile components, risking burnout, instability, and power drain. To him, it meant survival, but the logic was sound. The sergeant had noticed that many tube failures occurred not in flight but during ascent, when the rapid drop in pressure and temperature shocked the filaments. If he could stabilize that transition, he could keep the circuit alive. Without authorization, he began experimenting after hours. He modified a damaged SCR-522 radio set, wrapping fine copper wire around its tube housing and connecting it to a regulated low-voltage circuit, creating, in essence, a primitive thermal jacket. The result? On the ground, the modified set worked perfectly. At simulated altitude, it kept transmitting for twice the normal duration. Still, his officers dismissed it as unsafe. Too experimental, too dangerous, too unproven. But the idea spread. Other radio men began copying the modification in secret, testing them aboard non-combat flights. Soon, scattered reports reached Wright Field and the Radio Research Lab. Field-modified sets operating successfully at high altitude. This grassroots innovation, born not from a factory, but from a hangar bench, hinted at a solution that science alone hadn't found, and as 1944 dawned, the need was greater than ever. The Allies were preparing for Operation Point Blank, the massive strategic bombing campaign meant to cripple Germany's industrial core. The success of Point Blank depended on one thing above all: coordination in the air. Without reliable radio contact, bombers couldn't navigate through enemy flak zones. Fighters couldn't switch formations to protect them. The operation's success, and the invasion of Europe itself, hung on whether someone could make radios work at 40,000 feet. In the shadows of official laboratories, that one reckless idea was beginning to prove itself. In war, innovation doesn't always come from laboratories. It often rises from the dirt, from men who have nothing but necessity and imagination. The story of the high-altitude radio fix was not a tale of polished engineers in white coats. It was a tale of grease-stained mechanics, working by lantern light, guided by instinct more than instruction. The human angle, the man behind the reckless idea. The sergeant at the center of this quiet revolution was no officer, no scientist, and no theorist. He was one of thousands of technical specialists drafted into service, men who could take apart a radio blindfolded and reassemble it before dawn. He had spent years repairing broken receivers on training fields, watching pilots come down furious after missions because they couldn't contact their squadrons. Each failure felt personal. When he noticed the glass tubes cracking from sudden temperature shifts, his mind didn't go to theory. It went to feeling. The cold bit at his fingers as he handled the frozen metal. He imagined what it was doing to those fragile circuits. Colleagues called him obsessed. He kept experimenting with heat levels, adjusting resistors by touch, timing the temperature rise to mimic the climb of an aircraft. His peers joked that he was trying to boil the tubes alive, but to him, reckless was simply another word for unafraid to try. In the biting cold, mechanics checked dials glowing faintly orange. The sergeant who had first wrapped copper wire around a vacuum tube watched from the edge of the runway. He wasn't flying, but his invention was. In hundreds of aircraft above him, the signal would either hold or vanish into static. At 0900 hours, the bombers lifted into the pale morning sky. As they climbed beyond 30,000 feet, the usual signs of radio failure began to appear: flickering needles, low crackle, signal fade. But this time the voices held steady. Formation Alpha, check frequency. Reading you clear, lead. All ships confirm. The words cut through the air like a lifeline. By the time the formation reached cruising altitude, the difference was undeniable. Every squadron leader reported stable communication. For the first time in months, the giant formations moved as one, precise, coordinated, confident. At 40,000 feet, the sky was thin and merciless. Frost formed inside the gun turrets. Breath fogged the glass. But the radios stayed alive, their heated tubes defying the stratosphere's silence. Below, the German radar stations picked up the swarm. The Luftwaffe scrambled its interceptors, Messerschmitt Bf-109s and Focke-Wulf 190s, to meet the bombers head-on. As black flak burst in the sunlight, the first wave of fighters dived in from above. Bandits high. 11 o'clock! The call came through instantly. Gunners swiveled. Fighters peeled away to intercept. For the first time, warnings and commands moved across the formation faster than the enemy could exploit confusion. When one bomber broke formation to avoid flak, the lead immediately called it back into position. When fighters tried to separate the escorting Mustangs, the bomber group relayed a course correction that brought the escorts back in seconds. The difference was stunning. Before the modification, such coordination would have been impossible. Radio silence had always left squadrons to react individually, each ship fighting its own small war. But now the entire formation behaved like a single living organism. The Luftwaffe pilots trained to exploit Allied confusion found instead a wall of synchronized defense. Every time they dived, the bombers shifted, their gunners already tracking the angle of approach, calling ranges, confirming hits cut together. Inside one B-17, radio operator Staff Sergeant Harold Martin later recalled, "It was the first time I heard every voice loud and clear, even at 40,000. Usually by then all I'd get was hissing and popping. That day it sounded like we were sitting in the same room." For the sergeant on the ground, those voices were proof. His reckless coil, once dismissed as dangerous, was holding the line between life and death at the edge of the atmosphere. As the bombers reached Berlin, they faced the heaviest air defenses in Europe. The sky turned black with flak bursts, fragments tearing through aluminum skin. In the chaos, several formations became separated, but this time they didn't vanish. Echo Group, adjust bearing 090. We're with you. Copy that. Visual contact regained. They regrouped in minutes. Bombs fell over the city's industrial heart, the rail yards, engine plants, and aircraft factories that kept the German war machine alive. The mission cost dearly. 69 bombers and 11 fighters lost. But for the first time, the bombers reached their target, delivered their payload accurately, and returned with full communication integrity. Commanders were astonished. Debrief reports described stable signals at maximum altitude, clear command relay, and no equipment freeze. The data confirmed what field rumors had been saying for weeks. The new heating modification had changed everything. That night, in a small tent at an airbase near Bassingbourn, the sergeant received a message on his workbench radio, a short, informal signal from one of the crews who had flown the mission. "She worked, Sergeant. Clear all the way to Berlin. You saved our necks." He didn't respond. He just sat quietly, hands trembling from exhaustion and pride. What had started as an after-hours experiment had just proven itself in the crucible of war, and at the highest point any human voice had ever carried in combat. By the next morning, the reports reached Washington and Wright Field. The U.S. Army Air Forces ordered an immediate review of the modification. Within weeks, production lines incorporated the design into every new SCR 522 radio leaving the factories. The reckless idea was now standard issue. But while the technical victory was secured, the true turning point was still unfolding, in the skies where thousands of men would soon rely on that innovation during the most intense months of the air war. By the spring of 1944, the new self-heating radio coils were no longer an experiment. They were standard. Every new B-17, B-24, and P-51 rolling off the lines in England and America carried them. The modification had a name now, Signal Stabilization Retrofit No. 7, but among the air crews no one called it that. To them, it was simply the warm talker. Every morning at Thorpe Abbotts, Kimbolton, and Bassingbourn before the bombers rolled out, ground crews would test the radios. Instead of the usual crackling silence at altitude simulation, the voice came through steady. "Radio check, loud and clear." Men smiled quietly. No ceremony, no speeches. But everyone knew that voice meant one more thread of safety stitched into a war that tore everything else apart. The results were immediate and profound. In March and April, the 8th Air Force lost one bomber for every 26 sent. By July, after full radio stabilization and long-range P-51 escort coordination, losses dropped to 1 in 80. The shift was not luck. It was communication. When bombers stayed connected, their formations stayed tight. Escorts could adjust to threats faster. Resupply planes could locate survivors. And most importantly, when chaos erupted, orders reached every crew before panic could. In the operations room at High Wycombe, generals pored over mission logs, astonished. What they were seeing wasn't just improved signal range, it was a new way of fighting in the sky. Before, air combat at high altitude had been a fractured affair. Each group fought isolated battles inside the same storm. Now, for the first time, the Allied air forces could behave like a coordinated machine. Command could reroute squadrons mid-air. Recon aircraft could relay live weather data to incoming waves. And rescue operations, once a blind search, became guided missions through precise signal tracking. On June 6, 1944, today, the beaches of Normandy erupted in fire and smoke as thousands of Allied ships and planes converged. Above the invasion fleet, bomber formations circled in layered waves, striking fortifications, bridges, and rail lines. Amid that chaos, clear radio meant everything. For many pilots, it was the first time they had ever flown such a massive operation without silence or blackout. Every command, from altitude corrections to target calls, cut through perfectly. General Eisenhower's air staff later wrote, "Continuous communication across formations proved decisive. Coordination between bombers and escorts over the beaches maintained structural integrity under unprecedented traffic density. In simple words, the system held the warm talkers kept the invasion sky alive." Meanwhile, the man behind it all, Sergeant Daniel Mercer, was still stationed in England. He had been promoted but not reassigned. His new title read, Technical Maintenance Chief Radio Section 401st Bomb Group. He never asked for recognition, but his workshop had changed. Now, visitors came daily, engineers from the Signal Corps, officers with clipboards, factory inspectors. They'd ask about his coil design, his insulation method, his temperature tolerance tables. He'd show them patiently the same way he had built the first one. By hand, one loop at a time, copper glowing faintly as it met the soldering iron. The irony was not lost on him. The smallest piece of wire in a B-17 had become one of its greatest weapons. By autumn 1944, the air war over Europe was reaching its climax. The Luftwaffe, weakened but still deadly, fought to defend a dying Reich. The Allies, now communicating flawlessly at every altitude, began striking with surgical precision. Refineries, munitions depots, railway hubs, and all were hit systematically. And every operation relied on synchronized timing made possible by stable communication networks. The radios didn't win the war by themselves, but they ensured every man, every plane, and every bomb was in the right place at the right second. There was one more test. December 1944, the Ardennes. The Battle of the Bulge. Fog blanketed Europe. Allied air power was grounded for days. When the weather finally cleared, Operation Restoration launched, a massive air counterstrike that broke the German advance. From Spitfires to Thunderbolts, from Mustangs to flying fortresses, thousands of aircraft took off under orders relayed by radio. Not runner, not courier. Across every signal band, the same thing happened, stable voice. Zero freeze, instant command. It was the final proof that the new communication system had become the unseen backbone of Allied strategy. After the war, engineers analyzed thousands of mission logs. They discovered that communication reliability in freezing altitudes had jumped from 62% in 1943 to over 97% by 1945. Loss rates during confusion events had fallen by nearly half. In quiet archives years later, one officer wrote, "Victory in the air is not measured in bombs dropped, but in orders heard." Sergeant Mercer never patented his idea. He returned home in 1946, worked briefly for an electronics firm, then disappeared into civilian life. But in the decades that followed, every military aircraft, from Korea to Vietnam, from the Cold War bombers to the first jets, carried his principle: thermal stabilization of communication systems at high altitude. A simple idea born from frustration in a frozen hangar had become part of aviation DNA. He died in 1972. His service record listed nothing remarkable, no medals beyond the usual, no citation for invention, but tucked inside a museum case in Dayton, Ohio, sits a copper coil labeled Prototype SCR 522 Thermal Stabilization Unit, designed by Sergeant D. Mercer, 1944. Field tested, first bomb group. Beside it, a simple plaque reads, "In war, every voice matters." Even the one that fixes the static. The Second World War left the world littered with ruins, but within those ruins lay the seeds of the modern age. Among the countless inventions that rose from necessity, few were as invisible, yet as transformative, as that small coil of copper born in a cold workshop in 1943. When we think of victory, we picture tanks, planes, and flags. But wars are not won by machines alone. They are won by connection, by the fragile threads that bind men across distance, noise, and fear. The radio was that thread. And at 40,000 feet in the thin air where even oxygen faltered, a single sergeant's refusal to accept silence rewove that thread stronger than ever before. His idea, to warm a circuit instead of waiting for it to fail, became more than engineering. It was a philosophy that in the darkest, coldest places, sometimes survival means finding a way to keep the signal alive. Decades later, the same principle guides the satellites orbiting above our planet. They too battle freezing vacuum and electrical strain. They too rely on self-heating circuits born from the same wartime lineage. From fighter jets to spacecraft, from intercontinental communications to the device in your hand, every stable signal carries, in some distant way, the echo of that reckless idea. Today, historians rarely mention his name. But perhaps that's fitting, because his legacy was never meant to be loud. It hums quietly in the background, steady as a heartbeat, the sound of connection that never fails, no matter how high, how cold, or how far from home humanity dares to go. And so when we hear the static clear, when a signal cuts through silence, that is his victory. Not in medals, not in glory, but in every voice that can now be heard. Archival radio chatter fades beneath the closing words. Roger that. Loud and clear.